In this video, we discussed another mode of heat transfer, radiation. Radiation is the transfer of heat by electromagnetic waves, and this mechanism of heat transfer works even if there is vacuum between the two bodies. For example, the energy that we receive from the sun travels through the vacuum of space, so conduction and convection do not work, but the energy is transferred by electromagnetic waves. You feel the energy that is radiated from the sun, or for example, from a charcoal grill. The heat current by radiation is given by what is called the Stefan-Boltzmann law. The heat current H radiation is equal to A E sigma T to the power 4. And in this relation, A is the area of the emitting surface, E is the emissivity of the surface. It is a number between 0 and 1. And sigma is the Stefan-Boltzmann constant, and it is equal to 5.67 10 to the minus 8 watts per square meter per Kelvin to the power 4. Now here is a table with a few values of the emissivity. A dark surface has an emissivity that is typically close to 1, and a shiny surface has an emissivity that is typically close to 0. So for example, polished silver has an emissivity of 0.02, and this is quite counterintuitive that shiny surfaces are not good emitters, right? And this is because emissivity is not the same as reflectivity. Right? Emissivity is about emitting electromagnetic waves based on the temperature of the surface. So remember, a good absorber is a good emitter. So in general, dark surfaces have emissivity close to 1, and shiny surfaces have emissivity close to 0. An example of the bad emissivity of silver is the thermos bottles. You want to insulate a liquid to keep it warm. And so you want to reduce all mechanisms for heat transfer. And one way to do this is to produce a layer of vacuum that will eliminate the heat transfer by conduction or the heat transfer by convection. And then you want to reduce the heat transfer by radiation. And so for this, the thermos bottles, they have a silver coating, and the silver has a very low emissivity, so it will limit the heat transfer by radiation. At the same time, silver is highly reflective, so all of the radiation from the outside will be reflected towards the outside, and all of the radiation from the liquid will be reflected towards the liquid. Now, everybody has, at a temperature T, radiates energy following the Stefan-Boltzmann law. But if a body radiates energy, then it is losing energy, and its temperature should then be decreasing. But at the same time, the surrounding also radiates energy, and some of it is absorbed by the body. And so a body will be in thermal equilibrium with the surrounding when the temperature of the body T will be equal to the temperature of the surrounding Ts. And at this point, the energy that is lost by radiation is equal to the energy that is gained by absorption. So H radiation must be equal to H absorption. And since T will be Ts, then H radiation and H absorption will be equal to AE sigma Ts to the power 4. But if we assume that the surrounding temperature is always at Ts, then the energy current from absorption is always the same, and so it always is going to be equal to AE sigma Ts to the power 4. And so the net radiation when the body is not in equilibrium is then equal to AE sigma T minus Ts to the power 4. And so in this relation, T is the temperature of the surface, and Ts is the temperature of the surrounding. Now let's do an example with the net radiation of the human body. The surface area of a human is about 1.2 square meters, And skin is a good absorber, so its emissivity is around 1. The temperature of skin of our body is around 30 degrees Celsius, so 303 Kelvin. And a typical room temperature for the surrounding is about 20 degrees Celsius, so 293 degrees Kelvin. And so we can calculate the net energy current from radiation, which is equal to AE sigma T minus Ts to the power 4. And we find about 72 watts. Right? So every second, we lose a lot of energy, in fact, about 600 joules, but we also absorb almost the same amount, a little less, in fact, and the net radiation is 72 joules per second. Now, the same type of calculation we can do for the entire planet. Right? The Earth receives heat from the sun. The sun's surface temperature is about 5,800 Kelvin, and at that temperature, most of the radiation is in the visible range. And so the atmosphere is transparent to the light waves that are in this visible range, so it will reach the Earth's surface. The Earth's surface averages at about 14 degrees Celsius. And at that temperature, most of the light radiated is in the infrared range. The atmosphere is mostly transparent to infrared radiation, except for a few gases like carbon dioxide that will absorb and re-emit the infrared radiation. Some of the radiation is re-emitted towards the space, but some of it is also re-emitted towards the Earth. And this is the greenhouse effect. And it keeps the atmosphere average temperature around 33 degrees Celsius. And it depends on the amount of greenhouse gases that are in the atmosphere.